So here we're looking at chapter 11, we're looking at thermochemistry. So what this is really about is kind of this relationship between heat, which we'll talk a bit more about in a moment, and how that correlates to temperature. By the end of this unit, you'll be looking at being able to calculate heat changes, being able to find new temperatures, and also figure out kind of what's going on in some of those details. So we're starting with 11.1. We're looking at flow of energy, which is heat, or heat is a form of energy. So to talk this, we need to talk what energy is anyways. So energy at its heart is just the ability to do work or supply heat. Now when you take physics, you'll deal more with the work side of this. We're focusing more on the heat aspect. The background behind a lot of this, because again, this is chemistry, we're focusing on chemical potential energy as the source of a lot of this, or simply just chemical energy. And this is energy stored in chemicals because of their various compositions. In other words, this is energy stored because of the chemical bonds in a compound. And because different substances have different bonds, different atoms, different types of bonds, different organization of bonds, different substances will have different amounts of this chemical energy. Heat. So this is kind of the heart of this chapter. Heat is abbreviated with a lowercase q for obvious reasons. And it is simply just a form of energy that is transferred from one thing to another if there is a temperature difference between them. And what we should know is that heat will naturally flow from a higher temperature object to a lower temperature object. Notice that heat and temperature, although not the same, are still related, and that's what we're seeing there. And thermochemistry is simply just this study of heat changes that occur during both chemical and physical changes. One of the things I like about this chapter is that thermochemistry is chemical versus physical agnostic. It doesn't matter. So to talk heat, one of the really critical things is differentiating between system and surroundings, because we're talking heat moving, because that's what heat does. It's again transferred between two things at different temperatures. And so nailing down these two ideas of system and surroundings becomes critical. The system is the specific single thing that we're looking at. That's where we're focusing our attention. If you have a problem and you're given a situation, and the system will often be the noun in that substance. A system can be as big or small as we like, depending on the problem. The Earth could be the system, or a particular carbon atom in a molecule could be the system. We just have to define it. Now, again, this being chemistry, we can often view system in a chemical reaction as the chemicals in the chemical reaction is the system. Now the surroundings is everything else that exists. Oftentimes we're concerned with the stuff immediately surrounding, hence the term surroundings, the thing that we're focusing on. Now together, because the system is the thing we're looking at, the surroundings are everything else, the system plus surroundings makes up the universe. Now, in thermochemistry, the heat flow is always from the point of view of the system. So what this means is if the system gives off heat, if the system gives heat to the surroundings, we say that heat is lost. If the system takes in heat, we say heat is gained. Now, as a note, this actually ties in with the law of conservation of energy. So if the system gives off heat to the surroundings, we have to ask ourselves, where does that heat go? Well, the system lost a certain amount of heat, the surroundings gained an equal amount. However much the system loses, the surroundings gain, or vice versa. Here we say the system takes in heat. So if the system takes in heat, it took in the heat, it gained that heat from the surroundings. The surroundings lost a certain amount, and the system gained an equal amount. Now this ties into our idea of endothermic versus exothermic. So if we have a system that gives off heat, that means the surroundings are gaining heat. That means the temperature of the surroundings will go up. This is considered a negative heat change because the system is losing the heat. And we call that an exothermic process. So we can think exo as outer, heat is going out. And again, we would often view this as a negative heat change. That's really important. Now that a system takes in heat, the temperature, that means it's gaining that heat from the surroundings. And the surroundings are going to lose heat. The surroundings are going to cool down. They're going to go to a lower temperature. This is considered a positive heat change, and we call that an endothermic process. Now, one way to kind of analyze stuff when talking thermochemistry is to remember that for the most part, we, as the observer, we are not the system in most situations. That means our experience is going to be that of the surroundings. So if a reaction takes place in a beaker and we grab hold of the beaker and it feels warm, well, because we're feeling warm, that means heat is going to us. If heat is going to us, again, we are warming up the surroundings, so that would be exothermic. That's kind of how you have to think about this. Again, we are generally not the system. So for instance here, would ice melting be endothermic or exothermic? Like pause for a moment, ponder, 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 ponder. So ice melting would be endothermic. To melt the ice, heat has to go into the ice. And we can think about it also, if we like melt an ice cube in our hands, how does that feel to us? Well, our hand gets cold. It gets cold, so systems are cooling, the surroundings are cooling down. We're the surroundings. That means we're cooling down. That means heat is going to the thing we're holding. Heat is going to the system, so that would make it an endothermic process. Now, when we're talking heat, we talk various units, and a common unit of heat is calories. Now, this is a term you may be familiar with, and it doesn't do us any benefit. So like when we say, what does it mean to burn calories? So when you exercise, in fact, when you move, when you live, your body generates heat. It's exothermic. And we can measure that heat in a unit called calories. And that heat comes from the chemical breakdown of sugars and fats within your body. Now, although there is a better definition, which you'll learn in physics, 1 calorie, notice the lowercase c there. 1 calorie is the amount of heat or energy needed to raise the temperature of 1 gram of water 1 degree Celsius. Now, unfortunately, because here in America, we do everything we can to avoid using the metric system, a calorie is different from a calorie. You might think, well, of course, the one on the right is uppercase C. Of course it's different. Well, it is actually different. An uppercase C calorie or a dietary calorie is actually 1,000 individual calories, or enough energy to raise 1,000 grams of water or 1 kilogram of water 1 degree Celsius. Now, the calorie is also related to this idea of the joule, which is the official SI unit of heat and energy. You all may also see, so the joule is a J. You may also see a kilojoule later on certain problems. And we can convert between joules and kilojoules. In class, that is not something I would make you remember. Now, this all gets tied together with this idea of heat capacity. So heat capacity is how much energy it takes to raise or change, because it could be going up or down, an object's temperature by exactly 1 degree. So different objects have different heat capacities. And this leads to a lot of consequences. This means 2 objects could have different amounts of energy, but have the same temperature because they have different heat capacities. What we generally see is that the larger the heat capacity is, the more energy it's taking to raise the temperature of that object. So one way we can think about this in a very common way is the larger an object's heat capacity is, the harder it is to change its temperature, either to raise it or to lower it. Now the problem is this is object by object. So there is no table that you can look at that would tell you an object's heat capacity, because mass plays a large role. For instance, a cup of water has a much greater heat capacity than a drop of water, and a swimming pool would be even more. And you can think about this like if you have a swimming pool and a cup of water exposed to sun all day long in the summer, the cup of water is going to be at a higher temperature. That's because it has a lower heat capacity. It's easier to heat up than the pool would be. Now, because there's no table that we can use in terms of heat capacity, it's not super useful. So that's why we developed something called specific heat capacity. So the specific heat capacity, or simply just specific heat, is how much heat it takes to raise the temperature of 1 gram of a substance 1 degree Celsius. Notice there's two changes here. There's this mass piece, as well as I turn object to substance. So now, because it's based upon that 1 gram business, we can tabulate different specific heats of different substances. So a swimming pool of water and a cup of water, because they're both water, would have the same specific heat because it's all per 1 gram. So let's do a calculation with specific heat. So specific heat, again, lets us know how much energy is needed to raise a certain mass of a substance from one temperature to another. Or this equation here. Now, because we are efficient here in chemistry, not lazy, here is the exact same equation in variables. So again, Q is heat, M is mass of whatever is being heated or cooled, delta T is change in temperature, and do remember that delta in math and science classes means final minus initial. So I'll do an example calculation with this. So we have a piece of copper with a mass of 95.4 grams. We're changing it from 25 degrees Celsius to 48, and it's absorbed 849 joules of heat. What is the specific heat of copper? We just need to use the equation. So I take my equation, I plug in the numbers in the problem, and I get my answer. And that's a pretty reasonable specific heat. Again, the higher the specific heat, the harder it is to heat up and cool down. That's also the lower the specific heat, the easier it is to heat up and cool down. And metal like copper has a real low specific heat. That's why we use it for like pots and pans. So in the last section, we talked about just what heat is. Here's how we measure heat. There's two ways to do this depending on kind of what information we have. So first off, we call the measurement of heat calorimetry. And because we are full of good terms for things, we do the measuring of heat. So we do calorimetry with a calorimeter. Mind's blown, I am certain. And all that a calorimeter is it's a device that we use to measure how much heat is absorbed or released by chemical or physical change. Now, there's different types of calorimeters, but what they have in common is they have to be insulated, because you want all the energy change to be constrained to the calorimeter itself. You don't want outside energy coming in. You don't want you don't want energy inside leaving. So, little bit of caveat, don't focus on this too much. Now, a lot of chemical reactions take place in the open atmosphere, which means at a constant pressure. If we are at a constant pressure, which we will be here at this level of chemistry, the amount of heat that an object has is the same as its property called enthalpy. So this statement here is what you just really need to know. So for our purposes, we can treat enthalpy the exact same thing as heat change. You may see a Q, you may see a delta H. Don't panic, they mean the same thing for this level of chemistry. So how do we use a calorimeter? This is a picture of a calorimeter. It's probably the most common. It's called like the styrofoam cup calorimeter, coffee cup calorimeter. So here we often use 2 styrofoam cups just for even better insulation. What we do is we put water in there. The water is critical. So we're adding the system to the water. The water has to be a known volume or mass. The reason why it can be either way is water has a density of 1 gram per milliliter. So if you have 50 milliliters of water, you have 50 grams. If you have 25 milliliters of water, you have 25 grams. We're going to measure the initial temperature and final temperature of the water. This is the weird thing with calorimeters. Everything is about the water, but the water is not the system. The system is what's in the water. So the calorimeter is actually giving us information about the surroundings. So you got to keep that in mind. So if the water, the surroundings gain temperature, that means the system lost, making it exothermic. And then we use this equation here. This equation is a variation on the specific heat equation we had on the previous slide. I call this equation MCAT, not cat. That's just wrong. No, MCAT. So in this case, Q or delta H is the heat change of the water. M is the mass of the water. C is specific heat of the water. And delta T is the change in temperature of the water. With the calorimeter, everything is in terms of the water. So this allows us to calculate the heat released or absorbed by the reaction by the change in the surroundings, aka the water. So let's look at an example of this. So we have 25 milliliters of water that contains some hydrochloric acid, 25 milliliters of water contains some sodium hydroxide. We put that in a calorimeter. At the start of the reaction, everything is at 25 degrees Celsius. During the reaction, the highest temperature was 32 degrees Celsius, and we want to find out how much heat was released. Now we know the heat was released because the temperature of the water went up. And again, the only way for the water, the surroundings, to have raised in temperature is if the system, the reaction, the hydrochloric acid reacting with the sodium hydroxide, if that released heat. And again, 1 milliliter of water is 1 gram, so I see 25 milliliters of water, 25 milliliters of water, so 50 milliliters of water total, which means 50 grams of water. We need specific heat of water. We look it up. That's in our book. That'd be given to us in a problem. We need the change in temperature. Again, that's final minus initial, so 32 minus 25 is 7. We just plug everything in, so 50 times 4.18 times 7 gives us roughly 1,500 joules or 1.5 kilojoules. Now, is this reaction exothermic or endothermic? So ponder for a moment, pause if needed. Well, in this case, the water, the surroundings, gained heat because the temperature went up. Because that tells me the reaction itself is exothermic. Now, another way to calculate heat besides the calorimetry is kind of the experimental way. We can use something called a thermochemical equation. And so in the last, we mixed hydrochloric acid, sodium hydroxide together. It was exothermic. We could show this reaction by including a heat term. Now, we want this in terms of full mole. And don't worry about the statement here. Now, since heat was produced, we can add heat as a product. So here we have a normal looking balanced equation, but we see this heat term there. Anytime we see a heat term included with the information in a balanced chemical equation, we call that a thermochemical equation. Now again, delta H is technically negative for an exothermic reaction, and we saw that reaction was exothermic. So we could also say delta H equals negative 60 kilojoules. So note, because it was exothermic, I could either include the 60 kilojoule term in the products, or kind of off to the side, I could write something like delta H equals negative 60 kilojoules. And we can treat that heat change just like we would any other product or reactant. And again, we call that a thermochemical equation. Now again, there's also a term heat of reaction. It's simply just the heat change for the reaction as written. There's lots and lots and lots of different types of heat of whatevers, and they're almost always, this is the heat change for 1 mole of whatever. So for that particular reaction, the delta H was negative 60 kilojoules, so the heat of reaction was negative 60 kilojoules. So that means for every mole of HCl and every mole of NaOH that react, they'll produce 60 kilojoules of heat. Now, if heat were absorbed during the reaction, then it's endothermic and the delta H would be positive. And if it's positive, if heat is being taken in, being endothermic, we would treat the heat term as a reactant. So we could see the heat term on the products if it's exothermic. We could see the heat term in the reactants if it's endothermic. So for example, this is the decomposition of baking soda. So this right here, sodium hydrogen carbonate or sodium bicarbonate, that's your baking soda, and we see the heat term right there. And because it's in the reactants, that tells me that this particular reaction is endothermic. Excuse me. Now, thermochemistry and physical states. It is vital when doing with thermochemical equations that we indicate the physical state of the reactants and products. That's because different physical states, solid, liquid, gas, have different amounts of actual energy, which changes the heat change of the reaction. So here are 2 examples. So decomposition of water. So we have liquid water up top, we have gaseous water at the bottom, but we see requires different amounts of energy. These would both be thermochemical equations because there's a heat term. Now as a note, when looking at this, that this is a positive delta H because it's endothermic. Heat has to be added. I could include that in the reaction. I'd include that in the reactants. But we can see that the gaseous water has a lower heat of reaction there, and that's because the gaseous water has more heat naturally, has more energy. And so it requires less heat change to make it decompose. There's other ones like heat of combustion. That's the heat generated by the complete burning of 1 mole of a substance. There's a table of these. You don't have to know these. These would be given to you in the problem. Blah, blah, blah. And now the return of stoichiometry, which I know is the thing you were looking forward to the most. So like heat of combustion, the water thing we saw was all delta H of 1 mole. What if we don't have 1 mole? But for instance, like the heat of combustion of carbon in the form of graphite is 394 kilojoules. That's exothermic, it's negative because it's burning. But what if we only have 20 grams of carbon? That's not 1 mole. Could we find out how much energy would be released when the carbon burns now? Yes, absolutely. We just use stoichiometry. So general rules of stoichiometry is, again, we take what we're given, we turn it into moles. Then normally we would do the mole to mole ratio. But with thermochemical reactions, instead of the mole to mole ratio, we're doing the mole to heat. So we can use that as a conversion factor. So in the case of carbon, 1 mole of carbon burning generates 394 kilojoules. So again, we start with what we're given. We turn it into moles. And then this right here is the mole to heat ratio. That piece we could also get from a thermochemical equation. If we had a thermochemical equation, the heat term would be that part right there, and the bottom part, instead of 1 mole, would be whatever the coefficient is of that chemical. So again, in stoichiometry summary, convert to moles first, mole to heat ratio. So this section, we're going to look at heat changes when we are changing state. So like going from like ice melting from a solid to a liquid, liquid to a gas, or vice versa. So imagine what happens when you put an ice cube on the floor of a warm room. Well, the ice cube, because that's our thing that we're focusing on, would be our system at 0 degrees Celsius. The floor and the air would be the surroundings. The ice will absorb energy from the surroundings and begins to melt. Now, here's the part that people may not know. That mixture, that melting ice-water system will actually stay at 0 degrees Celsius until all of the ice is melted. Only when the temperature of the water, only when all the ice is melted will the temperature of the water go up. So what we find with heat change is that if there is a phase change, temperature remains constant. All that heat is going to change the state, not to raising the temperature. So, looking at solid to liquid. So all solids will absorb heat when melting to become a liquid. The amount of heat required that's absorbed to melt 1 mole of a substance at a constant temperature is called the molar heat of fusion. And we can actually see that equation right there, Q equals N times delta H Fuss. N would be moles. The delta H of Fuss, or fusion, is the molar heat of fusion. It's just the value you look up. Likewise, we could reverse it. And the amount of heat lost when 1 mole of a liquid changes to a solid is called the molar heat of solidification, delta H solid. Now, because energy is conserved, the amount of heat that something has to lose to solidify is the same as the amount of heat it has to absorb to melt. So what we find is that these two values are the same. The only difference is one's positive, one's negative. Fusion is going to be positive because heat's going in. Solidification is going to be negative because heat's leaving. In your textbook, there's on table 11.3, there is various heats of fusion for various substances. These are not something you have to memorize. This is something you'd be given. Now, again, you will never actually see the heat of solidification. And that's because the heat of fusion, it's the same as the heat of fusion value, just negative. Liquid to gas, same basic idea. The liquids, when they absorb heat, will become a vapor. And that heat has to come from somewhere, so the surroundings become cooler. So vaporization is endothermic. And the amount of heat required to vaporize 1 mole of a substance is called its molar heat of vaporization. Very similar thing. Very similar equation to the last one. We could do Q equals moles times heat of vaporization. Likewise, there's molar heat of condensation, which is just the reverse thing again. And once again, yeah. And again, table in the book gives various heats of vaporization. You will again not see any heat of condensation given because it's the same value, just opposite sign. So condensation should always yield a negative value because there's that negative there, and that's because condensation going from a gas to a liquid is always exothermic. Now, heating curve. This is really interesting. So the idea here is we start with ice down here at negative 20 degrees Celsius, and then we heat it up. We heat it up, heat it up, heat it up until it gets to 0 degrees Celsius. Now, interestingly, while it's heating, we could actually calculate heat using MCAT. You look at the mass of the ice being heated, specific heat of ice, delta T, in this case, negative 20 to 0. Now, while it's melting, so once we get to 0, now we're talking that heat is equal to the moles times the heat of fusion. And that happens until it's all gone. Now, one difference between these two equations, or two differences, one, molar heat of fusion is almost always going to be in kilojoules, whereas heat in MCAT spits out joules, is this mass versus moles. Keep that in mind. Now, once all the ice is gone, and we know that from right there, now we're heating it up again, and once again, MCAT, because temperature is going up. Once we hit 100 degrees Celsius, now we're boiling, we're vaporizing. And while we're vaporizing here, we go to the Q is moles times heat of vaporization. And only once all the water is boiled can the temperature go up again. And then as we do so, we're raising the temperature of steam, and we're back to MCAT. So you could actually calculate the heat change of ice going from like negative 20 to like 140. This is entirely possible. So again, analyzing it, just did this already. Again, notice temperature increases only when you're in one state of matter. So that when we have pure ice, temperature can go up. Pure steam, temperature can go up. Pure liquid, temperature can go up. While we're going through a phase change, the temperature remains constant. All that heat is going into the phase change itself. So let's see, using heat of vaporization. So for instance, how much heat is absorbed when 24.8 grams of liquid water is converted to steam? So again, we're going through a phase change. So immediately I know that we're going to use Q equals N times delta H, in this case, vaporization. Now the problem is the N. N is moles. We were given grams. So we look up the delta H vaporization, it's 40.7. We're going to turn that 24.8 grams of water to moles, which is what I'm doing right here. You could actually do this as two separate steps. So this is just turning the grams to moles. Then I would multiply by 40.7. You can do it as stoichiometry. You can do it as two separate things. Personally, I'd probably do it as two separate things. Another example of this is heat of solution. When something dissolves, there's a heat change. And so there we can do heat of solution. We treat heat of solution, the amount of heat change when 1 mole of something dissolves, just like we dealt with the other heats. It's heats of whatever. And I mentioned before, there's like heat of combustion, heat change when 1 mole of something burns. Heat of solution is just another example of this. A great example of this is like if we dissolve 1 mole of sodium hydroxide into water, it actually generates so much heat that it can actually start causing the solution to steam. So that'd be an exothermic reaction. Some are exothermic, some are endothermic. And again, calculation-wise, it's handled just like the previous molar heats. It's again Q equals N times delta H. So here in our last section, we're going to look at a couple more ways to calculate heat change non-experimentally. So we saw calorimeters are great for experimental. We saw thermochemical equations, but what if we don't have that information? So that's where we're at. So like, for instance, we can find carbon in both the form of graphite and diamond at 25 degrees Celsius. Now, because graphite is more stable than diamond, we would expect diamond to turn into graphite. But fortunately, for those of you who own diamonds or your parents do, this conversion takes a very, very, very long time. So because that takes millions of years, we really couldn't measure the heat change involved in it, just not realistic. So there's different methods that we use to calculate heat change when doing it directly otherwise wouldn't work. Either too long, maybe too much heat change to measure safely, maybe too far away. So one way we can do this is with something called Hess's law. Hess's law is pretty straightforward. It basically says if you add two or more thermochemical equations together to give you a final target equation, then you can also add the heat changes to give a final heat change. So here's an example. So here are two reactions. Now again, with Hess's law as a note, you would be provided the reaction itself. These two are given to you. Now, if I just add these up directly, it's not particularly helpful because we'd have carbon graphite on the left, carbon solid on the right, or diamond on the left, 2 moles of oxygen, 2 moles of carbon dioxide. Not super useful. But if I take that first equation and reverse it, it becomes this. Now notice when I reversed it, I actually switched the sign on the heat. That's because, again, energy is conserved. Now, if I add up the equations, just like I would two systems of equations in math, so again, there's the first one, there's the second. I add them up, this is what I get. So again, diamond, diamond, oxygen, oxygen, carbon dioxide, that's it for the reactants, and then carbon dioxide, oxygen, oxygen, graphite, graphite. So everything's there. So I've added the equations together. Now, just like a system of equation problem in math, Hess's law says I can also add their heat changes together. So that means the overall heat change would be negative 1.9 kilojoules. Now, why would we do this? How does this come into play? Well, notice here the oxygen on both sides, so it cancels. Carbon dioxide on both sides, so it cancels. So we could write it like this. So this is a way to figure out the heat change of a diamond turning into graphite without waiting millions of years in a calorimeter. Now again, one thing I want to stress. To do Hess's law problems, you have to be given the original equations. It's not something that you would be expected just to figure out on your own. Now, some reactions will give products besides what you want. So let's say you want to find the enthalpy change for the formation of carbon monoxide from its elements. Carbon plus oxygen is carbon dioxide. You want to do that reaction. Although it's an easy reaction to write, the reaction itself is nearly impossible to carry out in the lab because you're going to be making carbon dioxide as well. So again, nearly impossible to actually measure. So using Hess's law, we can figure this out by reactions that can be carried out in the lab. So again, here are two reactions. So up top is our target equation, and then I'm given these two reactions. Now, what we want to be able to do is to be able to add these equations up so that when added, they make the target equation. Now, the way that I do this is I try to identify something in each equation that is unique to the target equation. So like with the first reaction, I see this carbon graphite, because that's the only equation that has that. Now I see in the target equation, it's there in the reactants and 1 mole. I see in the reaction I have, it's there in the reactants in 1 mole. So that equation I can probably leave alone. Now, the second equation has carbon monoxide. And there, carbon monoxide's a reactant, but here it's a product. So that's going to tell me I'm going to reverse that second equation. And when I do that, that would allow me to then add them up together and get the target equation. Again, don't worry about where the equations are coming from. They are provided to you. So again, what you need to know, you should be able to, if given an overall equation and the partial equations, be able to reorganize them and add them together to get the final desired equation, and then understand conceptually what Hess's law is. AP Chem deals with this a lot more. You don't have to worry about too much right now. Now, the other thing we can do, which is kind of a consequence of Hess's law, is called heats of formation. And sometimes it's just way too hard to measure the heat change for a reaction. Like the materials may not be available, could be too slow, could be too expensive. So what we can do is we can calculate what the enthalpy change is from something called the heat of formation. Now again, heat of whatever is just the heat change for 1 mole. So heat of formation is the heat change to make 1 mole of a compound from its elements. So like if we were making carbon dioxide, so if we were looking at the heat of formation of carbon dioxide, we'd be making 1 mole of carbon dioxide from its elements, oxygen and carbon. Now this is assuming everything is in their standard states at 25 degrees Celsius. Now, as a note, the standard heat of formation of an element in its standard state is set at 0. Well, why is that? Well, you have to remember, heat of formation is the heat change to make something from its elements. If it's already an element, it takes 0 heat change to make something from itself. So for example, if I was making oxygen gas, it takes 0 heat to turn oxygen gas into oxygen gas. So really, if you don't see an element on a table, it's probably 0. So these are examples of that. There's been a lot of values for heat of formation in your book. This would be given to you on a quiz. And they're useful when we're calculating standard heats of reaction in standard conditions. And that's just because you simply just add up all the products, you add up the heats of formation of all the reactants, and then it's products minus reactants. Add up all the products, add up all the reactants, products minus reactants. So this allows us to find the enthalpy change during reactions based upon the enthalpy change of the whole. So for example, what's the standard heat of reaction for the reaction of carbon monoxide gas with oxygen to form carbon dioxide? So we start with our balanced equation. So looking at this, this is not currently balanced. So we need to do that. So I see 1 carbon on the left, 1 carbon on the right. I see 3 oxygens on the left, 2 oxygens on the right. So I'll put a 2 there and a 2 there. So this is now balanced. So we're going to use the table in the book to find the standard heat of formation for each product and reactant. So the heat of formation of oxygen is 0. Again, that's a pure element. Heat of formation of carbon dioxide is negative 393.5. Heat of formation of carbon monoxide is negative 110.5. So we just kind of write those down. Now, we're going to add up all the products, add up all the reactants, taking into consideration the number of moles. So for instance, like with the carbon dioxide here, because it has a coefficient of a 2, that means I need to multiply it by 2. Same with the carbon dioxide. So that's what I do there. So I took that carbon dioxide, multiplied it by 2 because of the 2 right there. I took the 1 mole of oxygen, 1 because its coefficient is 1. Carbon dioxide is a 2 because of that. And then I just add up products minus reactants. There's only 1 product, the 2 moles of carbon dioxide, so negative 787, minus the reactant values that I had added together, and I get my answer. And I should expect that to be an exothermic reaction because it's negative.